Recording on. Okay. Plan for today. Yesterday, we introduced our beginning concepts dealing with mechanics. We talked about the 4 questions that we want to answer if we're talking about describing the motion of the object. For today, something to write with, your outline from yesterday, and then new tray or new sheet over on the red tray if you haven't picked one up. Let's get those things together quickly, and we will get started. Okay, so yesterday we started our discussion of mechanics. We talked about mechanics being the introduction to motion, or the study of motion. And we said that when we're studying mechanics, there are 4 things about that motion that we want to know. Yesterday, we talked about one of those things. That question that we were looking for is, where is the object? Okay? First thing I want you guys to do is, for 30 seconds, with each other, discuss similarities and differences for 3 terms: position, displacement, distance traveled. How are they similar? How are they different? Discuss. Okay. To start off for today, the problem set that I gave you. At the top of the problem set, I believe it says motion diagram number 1. Motion diagram number 1 shows you the location of an object represented by that circle at different times, which are labeled as T1, T2, T3, blah, blah, blah. Okay? So first, number 1 says write the value of the position vector. T equals 5 seconds. So what's position? What did you guys discuss as far as position goes in your little short discussion there? Where it is, where it's in relation to a reference point. So we have to make sure that we're including that, where it is relative to a reference point. So in this case, where is our reference point? Where are we making all of our measurements from? 0. This is going to be our reference point right here, the 0 meter mark. Okay? So in this case, when it says what is the value of the position vector at t equals 5 seconds, right? It would start off, well, here's t equals 5, right? Okay, so we look and find that the dot is right here. So what would our position vector be? It would be 4 meters, but does that really tell us where that object is? Okay? There's a lot of things that could be 4 meters away from that reference point. What else do we need to include here? Some kind of a direction. How would we distinguish? East, we could go east if we wanted to. We could go right if we wanted to. Another way that we could look at it as well might be, a lot of times if we just have a number line like this, we could call one direction positive and one direction negative. We could distinguish that way as well. Okay? Next, displacement. It says, what is the displacement of the object between 3 seconds and 8 seconds? So, in your little discussion, displacement. What's our definition of displacement, or what is the displacement of something?
The amount of distance.
No, not the amount of distance. The change in position, okay? It's not the distance that it travels. That's something different, okay? So, in order to calculate the displacement, first, we use the notation delta x usually, okay? The delta representing the change, and then the x representing the position, okay? In order to calculate the displacement of an object, its change in position, what do we need to know? So, say more generally, where it starts and where it ends, right? And so we look at x final minus x initial. Where did it start off versus where did it end up? Okay? So in this case, right, the final condition is going to be where it is when? At t equals 8. So we look on our graph, right, we see that t equals 8 is 11 meters, okay? Except we should probably include that it's 11 meters what? East. Or positive, if we want to call it that way. Could do right as well.
Why is that 11?
So here's t equals 8, right? Okay, and then there's the dot at t equals 8, and it's at the 11 mark. Next, the initial condition. Where did it start? In this case here, not at the very, very beginning, but when?
3 seconds.
At 3 seconds. So we look here and we find 3 seconds, right? It's right there. So its initial position was what? 2.5 meters east. Okay? So we do our math and we end up seeing here that the displacement of this object was 8.5 meters east. Because, okay, well, because they're both east, but more generally, Kennedy, we talked about yesterday that displacement was something that we referred to as a vector quantity, right? A vector quantity has to tell us two things. Do you remember the two things the vector quantity has to tell us? Magnitude and direction, right? How much and which way. So as far as displacement goes, we know how much, we know how far this object went, but now by throwing the east on it, we also know which way it went. All right, are we good there? All right, so let's pick it up from here. We talked about scalar quantity yesterday, right?
Yeah.
Okay, so scalar quantity, unlike a vector quantity, is how much only. It's only magnitude. So distance traveled, right? First, what was our definition of distance traveled in your little discussion group there? Total path, right? Doesn't really matter which way we go or whatever. We're just adding up distance. Distance traveled is a scalar quantity where we just keep adding and adding and adding regardless of which way we're going. All right. There. So we talked about study of motion. 4 questions. Yesterday, we answered the first question. Where is the object? We talked about, where is it right now versus where is it, in a moving situation. Okay? The second question that we want to look at is, well, you better get it. There it is. What is that object doing right now? Once again, we have a couple of different options as far as describing what is that object doing right now. So let's talk about the first one. Speed. I'm assuming most of you have at least heard of speed or are familiar with it somehow, some way. As far as the definition goes, speed is the rate at which distance is traveled. Just in general, when we talk about something being a rate, that implies that it's connected with something. When we talk about something being a rate, Lauren? It's usually a fraction, but there's usually something on the bottom of that fraction. Not always one. Time. When we talk about something being a rate of something, it generally implies that it's over time. And in this case, speed is the ratio of the distance an object moves, so distance traveled, and the time it takes to move that distance. When we describe something as a rate, that implies that there's a time factor in there. Speed, specifically, is the ratio of the distance traveled and the time it takes to move that distance. With that being the case, how would we calculate the speed of something?
Distance over time.
Distance traveled over time. So it would look like this. So calculating the speed of something is taking the distance it travels divided by the time it takes to travel that distance. As far as a unit goes, what are we going to measure distance traveled in, SI-wise? Meters. Okay. What are we going to measure time in? Seconds. So the unit for speed, SI unit, is going to be meters per second. There are other ways that we can measure speed, but SI units, it would be meters per second. Good there? Okay. You have this picture underneath our discussion of speed. Picture of a girl running a race. If you look closely, she has a little ponytail back there. So, yeah. that
So it's
way,
the
girl.
difference between a guy and a girl.
Yep,
He
it's-
is a
it's
guy
stick-
with long
It's stick
hair.
figures. I know. That's rather sexist, I know. Alright. So to calculate the speed of this runner, we have to know two things, right? What do we have to know in order to calculate the speed of this runner? Distance traveled and the time. So what's the distance traveled, at least for this portion of the race that we're looking at here?
95.
So, well, we only have a time right here, right next. So the distance that it's traveled, at least in the time that we have, is how far? 50 meters. Okay, 50 meters from zero. Although, Sam, if we're talking about distance traveled, right? Now, if we're talking about distance traveled, it doesn't matter which direction we're going. Okay? So, 50 meters, right, is the distance traveled, divided by, in this case, so 50 meters, right? Speed is equal to distance over time, right? So 50 meters is the distance.
So it doesn't matter, like, right?
No, in this case, no, because it's just distance traveled. Okay? But then, how long does it take to go this 50 meters? 6 seconds. Okay. I guess we don't really for sure, but we'll assume that it is. Okay. It's about a 12-second 100-meter dash, or probably a little less than 12, which is pretty decent, you know, especially for high school.
I thought meters were like, I was thinking miles, and
No.
at first I was like, oh.
So, when you calculate that out, you end up with 8.3 meters per second. It is repeating all the sig wise, if we don't really know exactly measurement-wise how many sig these things have, so we'll go with that. Okay. Is that good for speed? Okay, now, not to confuse you, but let's talk about velocity. Okay. Most of you probably use speed and velocity interchangeably, but they are not. They are actually two different things. As far as the definition goes, velocity is the rate of displacement of an object. As far as a better description, the average velocity is a ratio between the displacement of an object and the time it takes to complete that displacement. It's a ratio of the displacement of that object and the time it takes to complete that displacement. With that being said, the formula for velocity would look like this. Notice it's a little different, right? At the beginning of class, you distinguished between distance traveled and displacement. They are two different things. You can get rid of the, if you want to, you can get rid of the average part here. I call it E. Once again, as far as the unit goes, though, right? What are we going to measure displacement in? Meters, okay? Time's still going to be measured in seconds. So that means our unit's going to be meters per second.
Why didn't that little triangle?
For every little triangle is delta, right?
Yeah,
Okay. Because it represents change, right? That's what we use to represent change. And displacement is a change in position. Where do we start versus where do we finish? One thing before we take off, I know time's getting really short, but I want to finish this part here. Okay? So, last thing about velocity, well not the last thing, but velocity is a vector quantity. And that means it has to tell us what? Magnitude and direction. In this case, the magnitude is going to represent what? Not distance. The magnitude of the velocity is how fast is it moving, or the speed that it's going, but the velocity also will include what? Not only how fast, but also which way it's going. Is it going right? Is it going left? Is it going east? Is it going west? That's the vector part. Guess what? Nope, that's the displacement. Those are two different things, right?
But the delta, does that have anything to do with the problem? Like,
Well,
there's no